Hey, thank you so much for making the time. I'll try and keep this chat as short and interactive as possible. Um, my name is Vishnu. I'm one of the co-founders of E6 Data. Some of my colleagues and co-founders are all here, so would be excited to chat with all of you. I'm going to talk about our approach to building a new breed of distributed compute engine, something that is Lakehouse and object store native from scratch. Why we chose to do this, what choices we made or trade-offs we made, and what we learned along the way. We have a Q&A session at the end, so I'll try and take all questions then. But if something seriously major pops up, please interrupt me. We can always take the question then. So very quickly, a little bit about our story. This company was born out of Bangalore in India, just a few kilometers from here. We're based on Infantry Road. And so we were inspired, I guess, by the urge to build world-beating data infrastructure and compute infrastructure software from India. Obviously, the waves that came before us have shown that we can build world-class SaaS, massively scalable platforms across gaming, e-commerce, marketplaces, every other category imaginable. And I think we were excited by the opportunity to do data infrastructure. We very carefully assembled our early team across a group of folks with outsider thinking, fresh perspective, as well as domain experts, since you can't do one without the other. Most of our customers are spread across US and India. Because of the nature of our product, they tend to be fairly large companies, either unicorns thereabouts or listed enterprises. We closed our Series A with Accel Partners, so how they got to know us was a lot of their early investees were users of the product. So Shaker, for example, was one of the first or the first investor in Freshworks, in ChargeBee, a bunch of other similar companies. So that helped them evaluate us, I guess. We're a young team, but growing fast. We're expected to cross 100 team strength by 25, but with a very heavy focus on the core engineering and associated areas. So what is E6 Data before we dive in and go into too much detail? I'll try and frame this in terms of something that is familiar. So this is your data platform or your data stack. Your top level is your application layer. You have an engine in the middle, Presto or Trino or Databricks or really anything that can query a data lake. You have surrounding building blocks like the Lakehouse format, which is a critical piece, the cloud that you build on, and of course governance and cataloging, things like that. Right, so where E6 Data fits is we're a compute engine. So that's exactly where we fit in the stack. So for select use cases that demand extreme performance, scale, concurrency, that's really where we fit in. So having established what we do and where we fit, why on earth does the world need a new engine, right? There's so many cool projects out there, some that have reached absolute global scale. Some of them, like Databricks, are $40–50 billion companies born on amazing open source projects. So why a new engine, right? So I think it goes without saying that some of these blocks still remain top of mind, right? Cost, performance, and scalability. And given the nature of the audience, I expect all of y'all to sort of deal with this on a fairly regular basis. So cost and performance, let's say, are functions of the efficiency curve of any engine, right? At a given cost, you get a given performance. At a given performance, you get a given cost. And there are some scalability limitations to this. But what we find is that even very mature data platform teams with extremely optimized sort of platforms still find this to be a concern. And why? It's just because your evolutionary environment is constantly changing, right? Your queries are growing. Each one is getting more complex, or on average, they're getting more complex. The data footprint per query is growing. People want access to live or near real-time data, which poses the whole problem of streaming data on lake houses and so on. And there are a class of use cases where you need to guarantee SLAs. Right? So all of this has a fairly exponential impact on compute cost, since they often occur in 2s or 3s. Right? So coming to performance, right? So if you look at like existing engines, and we're huge fans, and we've learned a lot from existing engines like Trino and Spark. What happens, right? So let's say if you were to give it like a very oversized cluster, in this case 512 executors, and basically the largest coordinator or driver that we could find, and you run, small queries one at a time, meaning it has the luxury of a full cluster to operate on, you'll see that engines are not very different, right? Like most are there or thereabouts in terms of performance. But as soon as you subject them to load, right? Like in this case, the form of load was 5 queries hitting the cluster every second. And these are all fairly small queries, mind you, right? Even this massively large cluster, you can look at like the degradation of 19x and 14x for the P95 latency. Now that is undesirable, right? Like this has direct implications on performance, cost, like business users and downstream data consumers complaining. So we felt we had the opportunity to build something that would degrade much more gracefully with scale. So that's one. And of course, rarely do you get a workload where it's a steady 5 QPS, right? Like it's usually bursty, it's usually messy, which is more similar to what you'll see here. So this was essentially what our motivation was and what sort of excites us, that sort of scale, complexity, load. We've tried to do this across different real-world scenarios with customers, as well as on benchmark data sets, simulating various real-world conditions like skew, etc. And the results sort of hold, right? Like, so for a given cluster configuration, building a different way, building a new engine with a different set of design principles can give you outsized performance benefits, right? Like you can see here that P95 is dramatically different. We've done this even against commercial, like best-in-class engines, like managed sort of Databricks using the SQL warehouses or the Photon engines, and similar results hold, right? So what I'm basically wanting to say is that if you build for a certain set of use cases or a certain class of use cases, you can make a certain set of design choices and like be extremely efficient there. Now, will this be extraordinarily good at tiny scale where there's no load? Probably not. You're better off with something else. But we feel that that top right end of the spectrum is untapped and is like something that leads to too much frustration, cost, and performance concerns, and that's where we have built for, right? So how this manifests in a use case is that, it's a better price performance curve, right? So for a given spend level, you get a jump in performance compared to an alternate approach. Or conversely, for a given performance target, you can get a dramatically lower cost, right? Like compute cost, which indirectly impacts like overall TCO. The other side of the coin is that if you need to guarantee a certain latency, regardless of the scale or QPS that you operate at, you can guarantee this fairly gracefully as opposed to, as compared to other cases. So this is sort of the world that we were building for, and these are sort of our goals as we chart out our roadmap and build the engine. So let me come to, like, as we get to the part of the talk now where we talk about how did we build this, right? Like I hope I've established why we built this, right? Like the motivation for building it. But now coming to how did we build this, it's important to first call out what we did not do too differently, right? So all of the cool stuff on this slide, like vectorization, columnar processing, pipelined execution, the efficient use of parallelism and distribution. These are concepts that exist and have been covered really well in academia. Most modern engines have already absorbed these concepts, or should, or will, or are absorbing these concepts. And even if you do all of these impeccably well, you will not move the needle beyond the state of the art too much, right? Like, so you will get percentage or very incremental gains depending on how well you implement. And as a young startup, you're never going to win by doing 200 things more flawlessly than the largest sort of companies in the world that do this. You have to really pick like what can make you sort of win, right? So let's now come to what we did do, in my opinion, very differently, right? One, before we get to the super different, you have to use what is like the best practices, right? Like all of the stuff that I outlined on the previous slide, but build it on new foundations, right? So all of this stuff, you cannot miss any one of these, and there's probably like dozens and dozens more. You have to do them well or well enough, but we had to build from scratch on our foundations. Now, what are our foundations, right? So we took a very, very different new approach to the architecture of the engine. So before outlining what that new approach is, let's just look at the various things that have to happen under the hood when you execute any job or query, right? Like this is something that any distributed compute engine has to do. So there's a bunch of query related stuff, right? Like you have parsing, planning, optimization, execution, all of that stuff. There's a bunch of things related to the distributed processing aspect, which is where should I schedule tasks, when does scheduling happen, how does coordination between tasks happen. There's a bunch of infra-related aspects, right? Like what's the state of the cluster, how loaded are different components like executors and planners and so on. And based on that, how do I make task scheduling or scaling decisions and so on. And finally, the actual execution management. How does data flow through an execution tree, right from, let's say, a table scan operator all the way up the tree, right? Like, so what's the control flow and data flow mechanism like? Right, so if all of these have to be done in any query, it's not like a new engine can avoid these. You have to still do them, right? But just let's look at the architecture of the state of the art, like that we learned from. Right, this is the reference set for us, right? So Presto and Spark, right? Like, and the same applies to a commercial version of these. It's built on the same architecture, right? You have a driver or a coordinator which is sort of sitting at the top, which receives jobs from a job client. Let's say it's a SQL query. And then you have a bunch of distributed executors or workers. And these are all typically defined in the context of machines, right? Like, so it's still a VM-centric world. So if you think of those different jobs to be done that we discussed in that previous slide, you'll notice one thing very quickly, right? Way too much happens at the top. Whereas the executors or workers are purely responsible for executing individual tasks and so on. So that's not bad, but that, in our opinion, we felt that it would prove problematic, especially at the scale, load, and concurrency that we were going to deal with. So what this also, a byproduct of this was that by doing too much, some of that stuff is stateful, which means that under load, this can't scale out. Right? So not only are you concentrating too many activities in the coordinator or driver, you're making it stateful, which means it can't scale out, which will have a host of downstream problems. Now let's look at what happens when you have load or concurrency or scale. So these different activities compete for resource. So this was all in the context of one query. Now if you have tens or hundreds or just like very task-heavy queries or anything that makes them compete with each other for resources, you can see that this is going to be problematic. Right? So this was one big finding for us when we thought about how would we conceptualize architecture if we were to start from scratch. Right? So the problems of this earlier model are sort of clear, right? Like performance bottlenecks, single points of failure, because every single query flows through those components, and inefficient resource utilization. Right? Why? Because if you hit a bottleneck, you often have to duplicate resources. The only thing you can duplicate is executors or workers, which are the most expensive resource. And often you do it even if your bottleneck is not really there. Right? So, so what we felt one had to do if you were to start from scratch or had the luxury of starting from scratch is break it all up, right? Like separate it, decentralized, disaggregated, and as stateless as possible. Right, so if there are 8 jobs to be done, you have 8 different sort of boxes on the slide here, right? So the top end entity, which is the planner and results set caching module, does only that one thing. It generates a plan, it spits out a plan. The metadata service does all of the heavy lifting around, schema related, file listing related aspects. You have executor pods. Everything is a pod in this world, right? Like, so it's a very Kubernetes native approach. You have a separate distribution service, a cluster monitoring service, identity and governance service. So you break everything up. So the benefits of this are that you can avoid that single point of failure, right? Like coordination, for example, can be handled in individual executors. So the different colors there represent one of the executors actually playing a transient role of being a coordinating executor for 3 different queries that hit the system at a certain point of time, right? As soon as they finish the coordination task, they dump like a task tree, let's say, into the distribution service, and then they go back to being a normal task executor, right? What this allowed us to also do is, and we also we had a stated goal of making everything that could be stateless, right? So, which meant that any component can scale, including the planner, right? Like which in the Trino or Spark world is like one big pinpoint. So there's one tiny red arrow there, which we haven't yet figured out how to scale. So I just thought we'll call that out. But apart from this, either we've already made all of these components scalable or we figured out how to, right? So this is one big sort of impact, right? What you can see here is that this is, for example, the pod count. You can see that the green here is the executor pods, and the blue is actually our planner pods. So you can see that there are phases where the executor scale but not the planner, and there are other phases where the planner scales but not the executor, which is life, right? Like different workloads have different loads that they impose on the system, and just that one component can scale rather than executors as a whole or the whole cluster as a whole. So this was something that we were pretty excited about. Second, by making these components sort of granular, we can also make scaling very responsive and fast, right? So different components can scale super quickly, both up and down, in response to load, and you can see how close to the load we are in terms of scaling. Next, and the last big point that I'll cover is the new approach to distributed processing. So again, starting with the existing approach, in, let's say, a Presto or a Trino query, you will find that when you're at the stage where you're ready to distribute tasks to executors, this distribution, which happens where you decide which task runs on which worker node, happens completely upfront prior to the start of a query, which means that you've already decided what should run where and how stuff is coordinated across the tree. And just as you say it like that, you know that for very complex queries with massive task parallelism and under a state of a system where you have many queries running at the same time, this upfront estimation can go very, very, very wrong, right? So this was one thing that we found, that especially when you have concurrency, scale, and complexity, this would be fairly brittle, or rather like it's a byproduct of the approach, right? The second was that there's one component that can scale out, workers or executors, right? So let's say you face load and you do scale out. And, but what happens is that the nature of this, this task mapping, which happens up front, does not recognize the new executors that have come on stream for ongoing tasks, for ongoing queries. So scale out will only benefit future jobs. So if you want to guarantee SLAs like P95, P99 on a query basis, this proves problematic. So yeah, so these are some of the problems that sort of come into this, heavy distribution overheads being like another one that's quite prominent. So what we did here was to say that you can't solve the problem, so let's avoid it, right? Like, so this decentralized, disaggregated approach allows us to, rather than having a central coordinator push tasks to executor pods will actually pull tasks from that queue whenever they have free resources available. So even if you have data skew, even if you have uneven task completion times, your executor pool is always at a high utilization, because as soon as it becomes free, it looks for a task available and then it grabs it and starts executing. So so a lot of these benefits sort of flowed from the first choice, which is the architecture, but we also built the execution model to be as dynamic and sort of just in time as possible without needing to do anything before start of execution. So smaller constructs that we use was, while the task distribution model is pull-based, the data flow model is push-based, right? So I've just got a slide here. I know I'm running out of time, so I'll keep it short. But essentially, how does data flow through a tree? You can see for most other engines, except for Snowflake, it's a pull-based model, whereas which means the top of the tree will pull data from the lower level operator, which then triggers its dependent operators all the way down to the leaf level or table scan operator. In this case, it's exactly the reverse. So it's much more like the internals of a streaming system. There's some interesting material here where the DuckDB folks, who we again learn a lot from, have published. So that's pretty much it. So where do these design choices come in handy? One, especially if you have large mutable data sets, lots of updates, deletes, And especially within that case, when you have complex, heavy operations, heavy query loads or concurrency, your use cases demand access to near real-time or live data, right, through streaming pipelines, and you have latency sensitivity. So in these use cases, we find that the price performance jump is particularly extreme, which conversely also does mean that if none of these apply and the data set is super small and you have purely mutable data, etc., there are other systems that you would choose. I mean, you'll all have a mental map for, I will use these classes or I'll evaluate between these classes of engines for this type of workload, right? So this is some of the inherent, or these are some of the implications of the inherent choices that we made. So yeah, what we're doing next is we're adding capability where we bring Lakehouse native vector search with all the scalability benefits, access to real-time data, and so on. We're trying to expand the personas and use cases that we can support. Another big one is later in the year, we'll be bringing in ingestion and ETL workloads as well. So yeah, that's kind of what we're up to. Yeah, I'll stop there. I hope I'm on time. Would love to take any questions you have.
So how push-based systems are different than the pull-based, like what you were showing? So like,
Yeah.
yeah, this one, like, how does the push-based are different than the pull-based? Like normally most are what you are seeing.
So I've tried to cover it here. Basically, it's in terms of how the control flow and the data flow works. In the pull-based, control and data flow originates from the central coordinator, whereas push-based, it would originate from the distributed executor pod. Data flows through the operator tree from the bottom to the top in a push-based model, whereas in the pull-based model, it's the volcano-style top-level operator pulling data from dependent operators.
Yeah, hi, this is Vikram from a startup called Revify. We do a cloud data warehouse optimization. The question is, like when you said that for the executor nodes will actually do the jobs and they will take the role of planning and other aspects as well. At that time, if while it's taking role, how do you handle, I know you highlighted the single point of failure in other systems, but during that process, what is the backup, right? If that node goes down at that particular time, how are you handling all of those things? And does it not add a lot of more complexity to your overall orchestration, your caching, and some of the other things? Because the decentralization comes at a cost, right? So how are you handling it?
Yeah, I know, absolutely, right? Like, so for us, what we found was that in the earlier approach, if something happens to your driver or coordinator, if it goes into a bad state, every query in the system, every task of every query in the system is affected. What we've tried to do is to say, let's reduce the blast radius of anything bad that happens, right? Like limit it to the queries or jobs that are executing on that executor pod or those collection of executor pods, right? And we try to make sure that even the task that it plays the role of a coordinating executor, we try to make sure that as soon as it plays that role, it transfers the coordination or the task distribution context into a separate component. And then it goes back to being a normal task executor. So yeah, the complexity is in implementing, but we feel that it it allows us to handle like parallelism and distribution quite elegantly.
One follow-up. And is that the same reason that one particular service you highlighted with a red arrow is not scaled out?
Not yet, yes. We have to, that right now we've found a way where even for huge workloads, even a small sort of pod sort of does the job. So we said that we can kick that problem down the road since it's not yet become a bottleneck. But yeah, we would want to make that scalable also.
All right, thanks.